The answer is yes, I can do digital signal processing on 8085. Then why don't we do it? We cannot do it because digital signal processing operations are typically done in real time. So general purpose microprocessors like 8085, they lack the architectural enhancements that enable digital signal process to signal processing in real time. So that is the reason we cannot use a general purpose microprocessor to perform digital signal processing operations. So DSPs use special memory architectures that enable uh, fetching multiple data or instructions at the same time. Many of you in the audience will be familiar with operations like FIR filter, finite impulse response filter, or IAR filter, or fast Fourier transforms. So the instruction set of CPU, the instruction set and the architecture of a DSP enable all these operations to be done in hardware, not in software. So many of you who are familiar with computer architecture or processor architecture, you know that any operation can be done either in hardware or software, right? Any operation that can be done in hardware can be done in software. So what is the difference? The difference is how quickly can you do it? Anything that is done in hardware can be done in real time, but anything done in software typically cannot be done in real time unless you're talking about a 1 gigahertz processor or 2 gigahertz processor or a processor with multi-core and so on. Okay, so to sum it up, uh, instructions like multiply and accumulate, which are very fundamental for fast Fourier transforms or FIR or IAR filters, these are implemented in hardware in digital signal process. Okay, so 20 minutes is over. I am wondering if I should pause for a minute and see if there are any questions or any feedback already.
Yeah, let us do.
There are some specific operations, right, in signal processing like fast Fourier transforms or implementing digital filters where you have to multiply two parameters and uh, add it to a different parameter in real time. So if the architecture of a chip takes several clock cycles to perform this, right, the operation itself may be completed, but it may not be completed in real time. See, for example, let's take the human voice, right? Typically, the bandwidth of the human voice is 8 kilohertz, although we all know that the human ear is capable of listening to frequencies in the range of 0 to 20 kilohertz, typically, right? However, if you look at a telephone, right, a telephone is not an instrument that is meant to transmit music, right? It's an instrument that is designed to transmit human voice, and in the telephone system, the human voice, the bandwidth of the human voice is limited to 8 kilohertz. So the circuitry used in a telephone system should be capable of converting the human voice, which is band limited to 8 kilohertz, into a digital signal in real time. So if you have a chip uh, which cannot do this, 8 kilohertz means 125 microseconds, right? So for every sample of the voice signal, I only have 125 microseconds to convert it into a digital signal, to process it, filter it, compress it, and transmit it. I only have 125 microseconds. So if I use a 8085 processor, right, it may not be able to do this in 125 microseconds, which means I cannot do this signal processing in real time. However, if I have a chip uh, whose architecture is optimized, and what do I mean by architecture is optimized is there may be parallel pathways between the CPU and the memory, right? I'm saying I need to multiply two parameters, right? So the CPU may have two paths, two parallel paths, one path to memory one and one path to memory two. Therefore, the CPU may be able to fetch both the parameters that need to be multiplied at the same time. Okay, so this is what I mean by architecture is optimized. Primarily,
Okay.
you may more than one path to access data. And 8085, there is no hardware multiply instruction. Here again, I challenge the students. How do you perform multiplication in 8085, where there is no hardware multiply instruction? So the answer is by repeated addition, right? Multiplication is nothing but repeated addition. However, a digital signal processor has a hardware multiply instruction. So in one clock cycle, I can multiply two numbers, whereas the same operation may take anywhere from 15 to 20 cycles on an 8085.
Good. Yeah, I think that same person, Nirav, had responded multiple addition as in response to your question. And
Okay.
another question was SIP versus SOC. Can you explain the difference? SIP versus SOC?
No, SOC is a term typically we use to refer a monolithic chip. And by monolithic, what I mean is there is only one silicon chip inside the package. So that silicon chip has all the entities or all the agents needed to implement a system, as in you have the processor, you have the peripherals, you have the interrupt controller, you have the watchdog, you have the analog peripherals. It's all part of the same silicon chip, which is packaged, right? That is what we call as an SoC, system on chip. System in packages, they take the die, the silicon die that goes inside the microcontroller, what we refer to as a system on chip. They take that silicon die, put it in another package, and they have a couple of other, let me go back to the, so this is the silicon die that I was talking about. In this example, this is an ARM Cortex A8 processor, right? So if you take this die, by the way, I'm not very familiar about this Cortex A8 chip. It could be just a processor with no peripherals on it, but it is also possible to take the silicon chip from a microcontroller and throw it inside this package and then add all this other support circuitry. You see what I'm saying? If you take this chip out and package it, put it in its own package, that becomes a processor or a microcontroller, right? So if you open that package, you find nothing else except this chip, right? But if you open a SIP, you see this chip, the silicon die, which is the processor, and you also see a lot of other support circuitry like memory, EEPROM, a low dropout regulator, and you also see a lot of passive components like capacitors, resistors, inductors, and so on, right? So,
so we go. Let's move on to the next question about curriculum.
Uh-huh.
In a computer science and engineering program, should we use microprocessor as a core course or microcontroller as a core subject?
If you say the course is titled computer science, I would lean towards a microprocessor.
Computer science and engineering, most departments are CSE.
Okay, I think there should be a balance of both, because typically computer science and engineering students, I mean, they could get into embedded systems field as a career option, or they could join a company like Intel or AMD, which make processors and are looking for students who are good in processor architecture. So I wouldn't exclude one in favor of the other. I think definitely both should be taught in equal measure. That would be my my opinion.
Let us go on, and later on we'll come back to any other questions. Okay, just go ahead.
Sure. Okay, so we talked about different types of chips. Now this is where we get into some of the practical aspects of embedded systems design, microcontroller based design. So the first part of my seminar, I usually give some perspective to students about how to choose a microcontroller for an application. So I tell them, okay, Suresh, you get a job as a hardware designer in ISRO. Your manager comes to you and tells you, okay, the next project I'm making you the hardware designer. So your job is to pick the right microcontroller for the project. How do you go about it? So there are lots and lots of parameters that we have to evaluate before we can choose a right microcontroller for a given application. And so I'll spend the next few minutes just giving a snapshot. And like I said, I'm trying to compress an entire semester worth of information in a PowerPoint presentation. So if there is any interest in any of the points that I talk about, you feel that, hey, this is something that would interest us, can we have a webinar dedicated to this topic? For sure, we can do that, okay? So I'm saying this because I don't want you to get a feeling that I'm rushing through too many things. I need to do that because I just wanted to give you a taste of some of the things that I can talk about. Just set the landscape, or I just want to show you the menu. So if there is any particular dish that appeals to you, we can spend more time at a later date, okay? So the first aspect that I'd like to talk about in choosing a microcontroller for a given application is the core. By core, we are talking about the CPU, the central processing unit, right? So core, there are different types. So you have what is known as a proprietary core and a popular core. So here I challenge the students with a question, okay? What is the primary difference between a chip made by one company compared to a chip made by another company? Let's say, for example, a microcontroller made by Texas Instruments compared to a microcontroller made by Microchip, okay? And the answer is the CPU, right? The core design may be proprietary. A TA microcontroller may use a particular designed core. Microchip may use their own design core, right? And what differentiates these two cores? After all, both can do addition, both can do multiplication, both can do shifting of data. So what differentiates these two chips? Well, what differentiates is the instruction set that is used. That will be different. So anytime you encounter a microcontroller with an instruction set that is tied to that particular architecture, tied to that particular family of microcontrollers made by that company, we are talking about a proprietary core. So what is the example of a popular core? Many of you would be familiar with a company called ARM, right? A very, very famous company that designs processor architectures and licenses that architecture to other companies, right? ARM doesn't make a chip by themselves. Rather, what they do is they design the uh, processor and they license the design to other companies who use that design in their microcontrollers. So almost every manufacturer, including Texas Instruments, we offer chips that use ARM cores. So yeah, at TA, we have our own proprietary core, but we also offer chips with the ARM core. So that's the first decision you have to make. Do I want to choose an ARM code device, or do I want to choose a microcontroller with a proprietary core that is tied to a particular company? And there are pros and cons with each approach, but we won't go into that. And the next decision we have to make is a single core or a multi-core device. So there are microcontrollers which have only one CPU, one processor, but there are microcontrollers which have more than one CPU. It could be 2, it could be 4, it could be 8. I heard some of the NVIDIA chips, they have 16 cores, 16 CPUs inside the same chip, okay? And then when you talk about multi-core, we talk about homogeneous multi-core and heterogeneous multi-core. So homogeneous is when you have the same CPU repeated more than one time, that's a homogeneous multi-core chip. You could also have a microcontroller which is heterogeneous in the sense it could have one proprietary core CPU and another CPU could be an ARM chip. And I'll show you an example for both, okay? This block diagram is from one of our device data sheets. I work in the group that is called as a C2000 microcontroller family. That is where I work at Texas Instruments. And this is a block diagram from the datasheet. These are all publicly available information. If you go to TA website, you can see all this information. So this is the block diagram of a microcontroller that is from our Delfino family. And you can see that this microcontroller has two CPUs, but both CPUs are of the same kind. Internally, we refer to them as a C28 CPU. And you can see that this has two CPUs, but both are of the same kind. So this is the homogeneous multi-core, right? And I want to show you an example of another chip, which is a heterogeneous multi-core, again from our C2000 family of microcontrollers. So one CPU is a C28 CPU, but the other CPU is an ARM M3 CPU. So this is an example for a heterogeneous multi-core, okay? So the next parameter that you need to evaluate is, do you need a chip with hardware accelerators, okay? What are hardware accelerators? A good example would be a floating point unit. You will be familiar with the concept of fixed point devices and floating point devices, right? And each architecture, they have its own pros and cons. We'll talk a little bit about that. But I just wanted to give you an idea of the different hardware accelerators that are available in our C2000 Texas Instruments C2000 family of microcontrollers. A floating point unit is something that all of you will be familiar with. It is an IEEE standard peripheral. Almost every microcontroller that you encounter with from any manufacturer in the industry will have a floating point unit that's compatible with the IEEE 754 standard. But our microcontrollers have some special hardware accelerators called control law accelerator, which is a CPU by itself, right? It's a 32-bit floating point math accelerator, and it can execute code independently of the main CPU, right? And we also have an hardware accelerator called Viterbi Complex Math and CRC unit. Those of you in the audience who teach communication theory, you will be familiar with Viterbi encoding. And if you teach signal processing, you know what is complex math, FFT, and so on. And if you teach communication theory, you will know what is CRC, which is used in communication protocols like controller area network, a CAN, or linear interconnected network, a LIN. CRC is used in many, many fields, right? And we also have a trigonometric math unit where trigonometric operations like sine, cosine, arctan, they are all executed in hardware, not in software, okay? So first, we looked at the type of core that we need to consider, proprietary core or popular core. And then we talked about single core or multi-core. And then in multi-core, we talked about homogeneous core and heterogeneous core. Now we are talking about hardware accelerators, right? So here's a little bit of interesting information about floating point that I always like to tell students. The advantage of using a floating point device is a wider dynamic range. So students have a hard time comprehending terms like dynamic range, so I try to use a simpler term. We can represent very large and very small numbers using a floating point architecture. This, the students are able to understand. So anytime we talk about signals, we talk about the dynamic range of the signal, right? What is the smallest value and what is the largest value? So floating point, it has a very wide dynamic range, right? So what is the disadvantage of using a floating point architecture? The quantization is not uniform across the entire dynamic range, right? So the distribution is not uniform. So the precision of the numbers, it's greatest near zero, but as you move away from zero on either end of the number line, the precision becomes lower and lower. So less precision the further you get away from 0, right? So the next parameter that I'd like to talk about is memory. Memory is a very, very interesting topic. We can do a webinar exclusively devoted to memory, but we have just one slide about memory. So this is a first question I ask students, and they almost always answer it correctly. What is the difference between volatile and non-volatile? They always know the answer. And then I give a few examples for non-volatile memory. We have the flash memory, which is what 99% of all the microcontrollers that are available in the market, they use today. I talk a little bit about the technical aspects of flash memory, but let's not do that. We barely have 20 more minutes. And ferroelectric RAM is a relatively new technology. It has been in vogue for the last 5 or 6 years. In fact, TI makes some microcontrollers with ferroelectric RAM. This is a pretty new technology with some very interesting properties. The access speed of this memory is very, very fast, and you can treat it like a regular RAM in the sense you don't need any special algorithms that you need to execute to write data into ferroelectric RAM. But it also comes with a downside, meaning reads are destructive. Anytime you read data from ferroelectric RAM, that data is quote unquote destroyed, in the sense that data has to be written again. Okay, and then EEPROM, students are very familiar with this, electrically erasable programmable read-only memory, and ROM. I also highlight to students that, again, these terms are not etched in stone, because technically you can say flash is an EEPROM, right? Flash is electrically erasable and programmable. So why don't we call flash as EEPROM? Well, these are just industry terms. These are just industry parlances. So when somebody says flash, I know what technology was used to build that chip. I know special algorithms have to be run to write data into flash. So when somebody says EEPROM, I know what technology is used to build that chip. I know I can talk a little bit about the characteristics of that device. So there is a reason I put these bullets in green, because they are reprogrammable. I can change the data. ROM is created by a mask. So ROM, by definition, read-only memory, is not reprogrammable. And then I talk a little bit about volatile memory, RAM. We are all familiar with it. But I don't talk much about DDR RAM or NVRAM. There are a lot of exciting things happening in the area of memory, especially if you have interest in enterprise servers. You might have heard about technologies like non-volatile DIMM, NVDIMM, non-volatile dual inline memory module, and so on. But typically, they are not used in the microcontroller space, so I don't talk about those things. Try to keep my discussion restricted to microcontrollers. Okay, so I think we are 40 minutes past the beginning. Should I pass now for any questions, or do I continue?
Just go ahead. Let's take a couple of questions. Okay, just hang on for a minute. I'll read out a couple of questions.
About is communication peripherals, how to choose a microcontroller based on communication peripherals. So here I'd like to challenge students about the difference between synchronous communication and asynchronous communication. So I'm sure you're, I don't have to explain all this. You probably have all this as part of your curriculum. I do like to talk a little bit about baseband and broadband, because I want the students to be able to differentiate a serial protocol. I want them to be able to identify if a particular protocol falls under baseband or broadband. So I talk a little bit about this, and then I in fact, I have a separate presentation called Communication Protocols in Embedded Systems. I once gave that presentation in Texas A&M University in their Doha, Qatar campus. if there is enough interest, we can do a webinar exclusively on communication protocols. So these are some of the common serial protocols that are used in microcontrollers, and most of you will be familiar with all these protocols. UART is a most common protocol. It has been there forever, right? Some of you may be familiar with RS-232 and RS-485, but it is very important to make the distinction that RS-232, RS-485, they all pertain to the physical layer, right? Whereas we are not talking about the physical layer implementation, rather we are talking about the protocol itself here. Lin, you may be familiar, it's a very commonly used protocol in automobiles, a very low cost, low speed serial protocol that is used in automotive applications. I2C, very common when you want to have two chips on a board to talk to each other. Serial peripheral interface, a very fast synchronous protocol. And then CAN. There is a lot of interest in CAN among colleges right now. If any of you are part of the engineer to engineer E2E network, the E2E forum of Texas Instruments, my name may be very familiar to you all. I know a lot of colleges, they use a lot of TA hardware in their projects. So a lot of students, they reach out to me over the engineer to engineer E2E forum with questions about CAN. So I see that there is a lot of interest in CAN in the embedded community now. So I'm very sure that in your lab, there are a lot of student projects based on CAN. I have been a lead support engineer for the controller area network in my group for the last 18 years. So if there is enough interest, we can have a exclusive webinar just on the CAN protocol. Just let Dr. Vedula know. And then USB, we all know what it is. We use it every day. And of course, Ethernet, without which this webinar will not be possible. Okay. Then I give a snapshot to the students about some of the control peripherals that are available on microcontrollers and what they are used for. And I want to readily admit that this is not my area of expertise. Pulse width modulator, I do know they are used in motor control. Now almost all control has become digital, so there are peripherals in our microcontrollers that enable the digital control of applications like motor control. We are talking about induction motor, brushless DC motor, and so on. Running algorithms like field-oriented control, sensorless control, and also digital power applications like DC-DC converters, solar inverters, and so on. So unfortunately, I cannot talk in detail. Like I said, this is not my area of expertise, but I do know a little bit about these control peripherals, and I just like to give a snapshot of this to the students. And the all-important analog peripherals, because we live in an analog world, as much as every gadget that we use in our life, whether it's your cell phone or your CD player or your computer or anything, any gadget that you can think of is digital, but our world is an analog, and human beings, we are all analog people. So we need peripherals that convert analog signals to digital and vice versa, right? Here, I always like to throw an interesting question to students, or it's not exactly a question, but it's just a perspective. All digital circuits are analog, right? There is really no true digital circuit in the world. What we really classify as a digital is, if you really get deep down, they are all just analog circuits, right? We just happen to operate in cutoff or saturation, right? We don't operate in the linear region. So this sometimes bring a smile in the face of the students. Okay, so analog to digital converters and digital to analog converters, and op-amp, the very fundamental building block of all analog circuits, modern microcontrollers, they usually have some programmable gain op-amps on chip. So we have looked at some of the peripherals a designer of a embedded system, some of the peripherals that he needs to consider before choosing the right microcontroller. And there are also other support circuitry like power management. When I showed you the image of the system in package, or even the SOM, system on module, you saw two ICs, PMIC, right? PMIC, power management IC. You saw LDO, low dropout regulators. Why is this needed? This is needed because typically modern MCUs, they operate with more than one supply voltage. The core, the CPU, may operate at one particular voltage, and the input output, the IO circuitry, which interface to the external world, they operate at a different voltage. So some microcontrollers may operate with 3 different voltages, right? But your board may have only one 5-volt input. So you need some circuitry to take this 5 volts, convert it into 3.3 volts or 1.8 volts or 1.2 volts or 1 volt, depending on the microcontroller. We need these DC-DC converters or low dropout regulators. And we also need some kind of what we call as an SVS, supply voltage supervision. So if the supply voltage goes below a particular threshold, the operation of the microcontroller is not guaranteed anymore. So you probably want to reset the microcontroller. So the SVS circuitry, they do these tasks, right? And then the all-important JTAG. Interestingly, I was giving a presentation in one college, and after the lecture was over, one student came to me and said, "Sir, you didn't talk anything about JTAG." I asked him, "Why didn't you ask this question when I was giving the lecture?" Then it dawned upon me that students should know at least what JTAG is. So I added this bullet in my presentation, and I tell the students that this is nothing but a port, a specialized kind of IO port, which lets an IDE, what is called as an integrated development environment. Some of you may be familiar with KEIL, KEIL. Some of you, if you're using TI process, you may be familiar with Code Composer. So these are all IDEs, right? So the JTAG is a hardware port that enables the IDE software running on your PC to communicate with the MCU. So it is through the JTAG, you load code that you want to run on the MCU, you load that code through the JTAG. And of course, you also get a lot of debug hooks like setting a breakpoint and so on, right? Okay. So I also like to give some perspective to the students about the different development platforms. This, of course, these are development platforms that are available. We have just 3 more minutes. I think I probably should stop here. And
I think that's a good idea. Yeah, let's. I mean, you've covered a lot of different things, and I'm sure the audience has got an idea what are the various things that you're an expert at, and so it might be a good idea now to just quickly ask a couple of questions. I'd like to get a sense of quickly from the participants. If you are a faculty member in computer science and engineering department, please text saying that you are. Yes. Okay. Are you a faculty member in computer science and engineering? All of you who are faculty members in computer science and engineering, please text. I know, yeah, some of you are still here. Many of you are still here. So can you just, because then I assume that others are not. So I just want to hear from each of you. There is no, I mean, there will be no next session unless you ask me the answer these 2 questions. Okay. This is the we just have to plan what is required. So are you a faculty member in computer science and engineering? Can you please text very quickly or not? This is not a, I don't know. Okay, so this I get a 1 yes, 1 no, one another yes, another no. So we got a mixed group. Electrical engineering. Okay, so there's a mix of people here. So I think that is that we have. So many of them electrical engineering rather than computer science and engineering. So I guess this is being instrumentation engineering. Yes, CSE. So they're also actually faculty members from different circuit branches, not just computer science and engineering. So that's good to hear that. So this kind of a course. Would you like to see a larger and expanded version in terms of a series of webinars in the form of a course? That's the next question. Okay. Would you like to see a series of webinars, which might be, and also maybe when Harish visits India, one location, have a face-to-face session for X number of days or whatever can be arranged? Would you like to, have that kind of a opportunity for that? I would like to see as many of you respond to this, please, so that I can get a better idea, because I was not able to create a poll. I should have created a poll and got that answer. I'd like to see all of you. Just please respond. Okay, so everybody likes the idea, Harish, that that this is something that needs to be continued. So we can discuss this offline. So you want to say, have any closing words?
No, I mean, I'm just randomly cycling through my slides just to give you a feel for what is in store. Anyway, I really enjoyed this, but like I requested at the very beginning, I really need your feedback. I want to know if this was useful, and if you have any suggestions about what I should be talking, or what I should not be talking, that will be very helpful. That's pretty much all I have.
Okay, great. So this is fantastic. Thank you so much for sparing your time on a early morning here
Sure.
in Texas. So I'm sure you have a long day ahead of you, and appreciate your time. And you and I can follow up and decide how to proceed further, because this is a very exciting and very important area for faculty and students in all the engineering colleges in India. So thank you. And for the participants, I will be sending on a follow-up email to get more feedback from you. So look for that. And with that, I will say, Jai Ho. Thank you, Harish.
Thank you, Dr. Vedula. Thanks for the opportunity.